So the Jordan matrix was used. So first we are using a 2 by 2 octonionic matrix with one octonion here. And its conjugate. So this is a number with 8 dimensions, for example. And E0 is 1. It's A1 is 0 plus A2, no, A0, A1 E1, A7, E7. And the octonionic units, E0, which is 1, E1, although E1 is I as a complex number, then you have JK. You can give them different names, but it's better to just give numbers, E0 to A7. So the Jordan, the matrix, will represent the coordinate in a 10-dimensional Minkowski space-time. And here it's t minus s and t plus s. So on the diagonal you have a real number, and here you have an octonion. So it's 10-dimensional. So these are the standard 10-dimensional coordinate, and an operation which lets this invariant is SL of 2O is the Poincaré group, or the 1-dimension Lorentz. So it's interesting to have this coordinate to be sure that it's invariant by this, because then we have gravity. So then that will be the coordinate. In fact, I will build from my each point in the E8 lattice with the ninth coordinate will be the O1 plus S, 9 coordinate. In my E8 lattice will be the space coordinate, and T will just be a number that I will increase each time I make an operation, an action on the E8 lattice. But now I need a little more information. So this is a 2 by 2 Jordan matrix. I will insert someone in the middle to make a 3 by 3. So I keep this here. And I insert a scalar field in the middle, which is generally named phi, and a spinor, psi1 or psi plus, psi minus here, which is also an octonion. And here, to have a Jordan matrix, this is not important, it is just the conjugate and the conjugate. So in fact, this part of the matrix, like this part, has no information. It should just be deduced by the other part to be a Hermitian matrix. So then, this is a Jordan matrix, which is encoded. There is one matrix like this at each point of the E8 lattice. And with the way I show with using the magic star, we can change the numbers in these matrices to make the dynamic. But it's not made in any, it's not made randomly. It's made in the way to keep a gauge symmetry. So we will keep the E6 gauge symmetry, which is containing the SO91 to have the Lorentz invariance, and it will also contain the standard model. So how I do this with E6 is by using, so this matrix is operated by a Jordan product, which is M1, this one, M2 equals, in fact, you use a standard matrix product, but anti-symmetrized, symmetrized. Sorry. So, because otherwise you have problems of non-associativity of the octonion, so you cannot multiply. So the standard multiplication of matrix with octonion is non-associative, but the Jordan product of these 3 by 3 matrices is associative. Then we can build a triple product, which is named the associator of the Jordan, which is M1, it's a comma parenthesis, so G is another Jordan matrix. So this is the associator, so this is M1, M2, M3 minus M1, M2, M3. Like the graph that Marnie shows with the associator. So this is a graph like this, and this is the other. So this is a Jordan triple product, and the action on E6 is defined by 3 matrices, and is this plus I this. And this is an action of E6 on Jordan matrix J, which could be complexified. In fact, J is, instead of having O here, it's complexified with a C, everything. Because I have a complex number here, I, or for me it's E1. So and this is E0. So this is the action of E6 on E6 on a complexified G, so G, C. But we can do the same with E7, and then the action is the same in the beginning, G, M2, and here we have a quaternion, E1, M3G, depending on 5 matrices. And so this is the action of E7 on G quaternionized. And we can check this because the dimension of E6 is 78, and it's parameterized by 3 matrices, Jordan matrices, which should be traceless. So the trace should be 0. So then for this one, we have phi
minus t or something
equals minus 2t a kind of scalar field which cancels the time just for these matrices. And here we will have 5 matrices, and so 3 dimensions are missing because the dimension of E7 is 123, but I forgot to precise that here it's not E1, E2, E3, it's the action of SU3 on this one. No, the SU2, yes. So we have to multiply its action of SU2, so we use another complex, an imaginary quaternion. So it will be A1, E1, E2, E2, E3, E3, depending on 3 real numbers, which will mix the E1, E2, E3 of these matrices. Just by multiplication, by quaternionic multiplication. So in fact, instead of E1, it's A1 times E1. So you say that this is Q from SU2, and in fact it will be QE1, QE2, QE3. And then when you have the result is in J cross H. So it's three-dimensional matrices with a quaternion on the diagonal and an octonion tensored with a quaternion here and here. And we can do the same with E8. So we'll do this here. Exactly the same. It's E0, M1, G, M2, plus it will be an action not of a quaternion but of two octonion. And in fact this quaternion is imaginary, so we will have two, I name this S for example, S1, E1, S2, with this matrix, M3, G, and S1, E7, S2, M9, G, and S1 is, for example, B1, E1 plus B2, E2 plus B7, E7. It's a totally imaginary octonion. S2 also. E2, 7. And in fact, this is a representation of G2. G2, which is 40-dimensional. So the total of this has 9 times 26 plus 14, 248. So it's a representation of E8, which is acting on a Jordan matrix in OO. Which is not totally E8, in fact, but pretty E8. So the result of this will give 9 matrices, 9 Jordan matrices. No, 8, because then I will do the inverse operation of tensoring with the octonion. I detensor, so I take this octonion, will give 8 projection to E0 to E7. So I give 8 Jordan matrices as the result. And these 8 Jordan matrices will replace the 8 matrices, the 8 vertex of the cube, the 8 matrices on the 8 vertex of my cube. So I'm not changing the center, but I'm changing all around with this action. And also, yes, to precise that where I get this quaternion, or here this 2 value of the J2, this is easy. So I have another with there, with this behind, and I have the center, which belongs to the third E8 lattice. So each color for one E8 lattice when I am somewhere in E8, and but I have neighbors also, because each triangle belongs to a grid of triangle. So that's why I will interact with some neighbors here. with this 6, 1. And now you see from where they come, these numbers, which compose G2, this imaginary octonion. S1 will be on the green. And in fact, I take only the centers of the Jordan matrices, which are on these 7 green points to build S1. And to build S2, I take the center phi field, the scalar field of the 7 Jordan matrices on these 7 points. And how I identify which correspond to E1, E2, E7, then I have to show that here, with my magic square, I also have a Fano plane, which is defining the multiplication table of the octonion. So, how I build the Fano plane? I know that E1, E2 equals E3, because this is a quaternionic identification, IG equals K. So I have to go to affect to this yes, it's there, E1, E2. I go from here I have 1, here I have 2, and then E1, E2 gives 3, and E3, E1 gives 2. I continue here. And by symmetry, if I have 1, 2, I will have 4, because there's a power of 2 to build the red triangle. And I have arrows always on the same direction. And then, because I have 3 here, I know that the XOR product of 1 and 4 is 5 here. And 4 and 2 is 6 here, and I have 7 in the middle, and then I have other arrows to go there to the middle, like this. So then I build the Fano plane of the canonical table of octonion from the magic star, and also I have the identification automatically of the different
We've got
vertex with
and this is the one we're using with the Cole-Fury's representation for the neutrino as well, which is where I want it in the center. So
yes, it's better to have 7 in the center.
Yeah.
So
yeah,
we have everything.
Yes. Everything. So, so there's a tetrahedron there, because you've got 2 points crossing the side there, and there's a center point.
Oh yes, you will have tetrahedron, yes, right.
Yeah, so that's good.
And that's really emerging from E8. It's just we have to to look from the good viewpoint, which is the 9-dimension coordinate, which is totally new, except that Coxeter made this, but it was forgotten. So we have to work with 9-dimensional coordinate. We have to take the good viewing vector. We have to color the 3A8 lattice to identify them. And then we get all the structure. The structure of the octonion is in fact encoded there in E8 lattice. And the structure of the E8 Lie algebra is encoded, which is more complex than the lattice. And all the subalgebra, like E6, E7, and because E6 has the standard model and the gravity, we have also the physics there. And all is based on Klee's intuition of the viewing vector from a tetrahedron. And also this shape in 3D, you see this is stella octangula, but in sacred geometry this is named Merkaba, the Merkaba, or Merkaba. It has a philosophical meaning, and it's used in Leonardo da Vinci, the famous, what is the name? The painting. No, with a man inside, yes, like this. I will do my Leonardo. You know this one? The Vitruvian Man from our friend Leonardo. So this is the Da Vinci Code, in fact.
Yeah.
We found the real Da Vinci Code.
Yeah.